Assalamualaikum, good evening, everyone. Continuing from where I'd stopped yesterday. Um, just to recap the previous example that we had done, which was a simultaneous question, had an applied force which was acting at a horizontal on a double mass system. We're still dealing with a horizontal situation here, but the applied force is now acting at an angle to the two masses. And what's even more important here is that the applied force is acting downwards at an angle. What you need to also understand is that although the applied force is acting downwards, the two blocks are going to be accelerating to the right. Now, they should have mentioned that somewhere in the question. Let's hope they do. It says a learner constructs a push toy using two blocks with masses 1.5 kilogram and 3 kilograms. The blocks are connected by a massless, inextensible cord, and the learner then applies a force of 25 newtons at an angle of 30 degrees to the 1.5 kilogram block by means of a light, rigid rod. So there's basically a rod that's pushing down on the 1.5 kilogram, causing the toy to move across a flat surface. I think by stating across, they mean across horizontally to the right. The coefficient of kinetic friction between the surface and each block. So here, the coefficients were given, which is 0.15. Will the learners that are in the three different groups just please put up a message in each of the chat groups and tell everyone to please attend these lessons, because we are now going to actually start off with the more difficult questions today and tomorrow. And I'm expecting everybody to actually be here. The coefficient is 0.15 for each. I'm not going to state Newton's second law. Please ensure that you learn the law off by heart. So that's going to be a theory question there. Calculate the magnitude of the kinetic frictional force acting on the 3 kilogram block. Now, I would actually start off with the free body diagrams. Although it's actually asked in 7.3, I would just go ahead and actually draw the free body diagram for each one of them. I just want to emphasize this again, that your tension force is going to be acting away from your masses here. It's something new to the grade 11s. They haven't done this before. And I just want to emphasize the direction of the tension. The other thing I want to emphasize is the direction of the applied force. The applied force is actually applied down at an angle like this, which means I'm going to break that applied force up into components when I draw my free body diagram. There's a kinetic frictional force acting on both of them, which means it would be opposing the motion. So there's the kinetic frictional force on the 3 kilogram, and there's the kinetic frictional force on the 1.5 kilogram. Right, let's start. Free body diagrams first. So let's start off with the 3 kilogram, because that's actually an easier one to draw. For the 3 kilogram, we're going to have your gravitational force acting downwards, your normal force acting upwards, the tension, and then the kinetic friction. So that's our 3 kilogram free body diagram. For the 1.5 kilogram there, so we're going to have the components first. Your Fy is going to be down. Your Fx is going to be running across there. You're going to have your normal. So I should actually make the normal a little more realistic. The normal is going to actually compensate for both the Fy and the Fg. You got your Fy acting downwards, and you're going to have your gravitational force acting downwards. I just want to emphasize this about free body diagrams. If you have both the forces acting in the same direction, please draw them next to each other as opposed to on top of each other so that you can see two distinct forces. You're going to have your tension acting back, and you're going to have your kinetic frictional force here. You can call this Fk or Ff. Please note that the kinetic frictional force will actually be different on these masses here. I just want to also emphasize something, especially to my grade 11s, because I think you guys are more urgent than the grade 12s. Most of the grade 12s are writing their paper on the 15th of March, which means they have slightly longer time compared to the grade 11s. The grade 11s are writing on the 8th of March, which is almost a week earlier. Boys and girls, we have got literally no time to waste, and hence this really intensive next couple of weeks of lessons. By next week, I actually plan to actually make a start with electrostatics, right? Because that's another big section, and we need to get going with that. So I got my free body diagrams. Calculate the magnitude of the kinetic frictional force on the 3 kilogram now, which is 7.2. Your kinetic frictional force is going to be equal to mu k multiplied by your normal. Here, your normal is going to equal to your gravitational force. So in place of N, your gravitational force is going to be mg. So you're allowed to do this in one go like this, which is 0.15 into 3 times 9.8. Anyone?
4,41.
But it's a magnitude. Yeah, so we don't have to give the direction there. That's just good enough. Draw a label free body diagram of all the forces acting on the 1.5 kilograms. So we did 7.3 here. And then calculate the kinetic frictional force on the 1.5 kilogram. Don't be fooled by this 3 marks. Although the other one was also 3 marks on the top, the first 3 marks on the top was far easier to obtain. Here, your normal force is not equal to your gravitational force. Which is 7.4.1. The first thing we need to do is we need to show you using an equation that your normal is equal to Fy plus Fg. Because of the component, Fn and Fg are no longer equal. So here Fn is equal to F sine theta plus mg. And your value for F, 25. Sine 30 plus mg, 1.5 times 9.8. What's the answer there?
27.2.
27.2 newtons. Now that we got the normal, we can proceed to calculating the kinetic friction, which is going to be your mu k times your n, which is 0.15 multiplied by 27.2. Kinetic friction now, please.
4,08.
So although the kinetic coefficients of kinetic friction were the same, the kinetic frictional forces were different for 2 reasons. Different masses, and you had a y component acting downwards. Now, this is one of the questions that I wanted to talk about because if you look at the last year, and I'm specifically talking about 2023, you'll find that most of the questions, the examiner did not ask the learners to find the acceleration. The examiner simply asked the learners to find the tension without finding the acceleration. And you may be wondering, so what does that mean, Mr. Hamid? It simply means that normally when you are working with a simultaneous equation, we normally solve for A first and then we solve for T. So in other words here, if essentially we can do it two ways. We can solve for A first and then solve for T, which is the routine way of doing it. But I would like to solve for T directly so that I improve the accuracy of my answer. In other words, I'm going to attempt to solve for T directly without solving for A first. Now, my matriculants will actually appreciate this because when we actually started at the beginning of the year, we actually did quite a few questions where we actually solved for the tension without solving for the acceleration. For my grade 11s, this is going to be new, I'm hoping. And I'm going to show you how we actually go about doing this. So what do? Exactly what we do normally. We draw the free body diagrams first, which we have. We basically use Newton's second law and we set up our two equations and then we attempt to solve for T directly. So it's not so easy here, but no, it's easier. Sorry, I'm making a mistake. So F net equals MA firstly. And we're going to do this for the 3 kilogram mass that we have here in the back, which is easier to work with. Remember, both of them are accelerating to the right. They should have mentioned this in the question, but they didn't. It's a poorly phrased question. So this is for the 3 kilogram. And your F net here is going to be T plus minus Fk. If there's something that you don't understand, because there's a large number of you here, please stop and I don't mind explaining it again. Your tension, we want to find. Your kinetic friction for the 3 kilogram was 4.41. Equals to 3a. I'm going to leave this as equation 1. Then I'm going to go to the 1.5 kilogram. Now the 1.5 kilogram is a little bit more intense because you've got a Fx, which is the positive force. And to that, you're going to add these two negative forces here. So it's Fx plus minus T plus minus Fk equals to Ma. Fx plus minus T plus minus Fk equals to Ma. Your Fx is F cos theta minus the tension minus the kinetic friction equals to Ma. We're now going to plug in values here. This was 25, I think, cos of 30 degrees, if I'm not mistaken. One last time to check that. Correct. I want to solve for T. Yes, question?
Sorry to disturb, but I have a question, sir.
Yes, sir.
Will the tension for the first mass of the object be equal to the tension of the second?
Okay, so the only time the tensions will differ if you got two different ropes. So the tension within the same rope is the same, but it's just in two different directions here. So the T going forward on the 3 kilogram and the T going backwards on the 1.5 kilogram is exactly the same tension. Yes, sir. And the acceleration
Thank
of
you,
the
sir.
back mass and the acceleration of the front mass is also exactly the same. These questions,
Hi,
by the way,
thanks.
are no problem, sir. These questions are highly mathematical. You can't afford to make an error anyway. You can see it's only maths here. It's filled with maths. So you have to be very accurate and you must be tracking every step all the time. Double check your answers, especially because of the volume of maths you're going to end up doing. Right? I like to keep everything crisp and clean. I don't like to actually have too much of decimals floating everywhere because it just looks very messy and it compromises the accuracy. The 1.5 kilogram, which is sitting here, had a kinetic friction of 4.08, which we could have taken from the previous question. We had to basically use that as a decimal though. And that will be 1.5a. Now here, if you sharp, you can clearly see what you need to do to this equation at this point. So you can solve for t and eliminate a. So your aim is to get rid of a and only have t's now. And this is the reason why I think this examiner was kind and he gave 3 kilograms here and he gave 1.5 kilograms here. Because you can simply take 1.5, double it, and you can get 3 on the top. So I'm going to take this equation here, which is equation 2 essentially, and I'm going to multiply equation 2 by 2. So I'm going to take this whole equation and multiply it by 2. So 25 cos 30 multiplied by 2 is 50 cos 30. Minus t multiplied by 2 is minus 2t. 4.08 multiplied by 2 is minus 8,16. And 1.5 multiplied by 2 is 3a. So this is my new equation 2. I've got 3a on this side, gentlemen and ladies. And I've got 3a on my right-hand side here as well. So I can now take these two equations, which have both 3a on the right-hand side, and I can equate them to each other. So this left-hand side here and that left-hand side there are now going to be equal to each other. And I can solve for t without solving for a. So you have to be pretty smart with the maths at the end of the day as well, right? Because we don't really teach you simultaneous equations, yeah. We expect you to know it from grade, I don't know, grade 9 and grade 10. So t minus 4.41 is equal to 50 cos 30. Note, I didn't put decimals for that. Minus 2t minus 8.16. I'm just going to take the 2t across. I'm going to make that 3t is equal to 50 cos 30 minus 8.16. And I'm going to take the minus 4.41 across, plus 4.41. You can plug that in on your calculator, and you can give me the answer for t now.
So 13.18.
So
So 13.
Sorry? 13,
1, 3.
sorry. And there we are. But I'm going to leave horizontal masses over here. Will horizontal masses come out? Grade 11s? They did come out last year. They just gave them a horrible question in grade 11 last year. For you guys, I'm going to do that in class with you. I need to move on. And this is the other scenario that you're going to get tested on. This is a super, super popular question in the exam, which I refer to a horizontal and vertical mass. Here you have one mass that's going to move horizontally. The 5 kilogram is actually going to be pulled across the table by the 3 kilogram, and the 3 kilogram is going to drop down as it moves. I would also like to introduce you to some equations of motion here, because last year when they tested this with our grade 12s and grade 11s, they were just thoroughly lost. They didn't know what to do. Right, so I'm going to take a question from last year's trial paper, I think, where they were forced to use equations of motion to get the acceleration and then from there work out something. But this one here is what I would consider to be a routine question. I also chose this because of its simplicity. There's no externally applied force in the system. And the reason for that is simply because these tensions that you have here are going to create the acceleration for you. For example, for the 5 kilogram, the reason why it's going to move horizontally across the table is because you're going to have a tension that's going to act away from the mass. When you have this new device here, where your rope runs over a pulley, you still have the same tension in the rope. The difference now is that the tensions are going to have just completely different directions. And if you're wondering, so how am I going to work out the direction now? Again, you can keep it simple and you can just remember that your tension acts away from the masses. Or even better, if you got a pulley, your tension is always going to act towards your pulley. By the way, away from the masses will become towards the pulley, as you will see. So there's your tension, and there's your tension there. It's still the same tension. And again, the question you may ask is, why is the tension the same? The tension is simply the same because it's the same rope. It's one singular rope, and hence it has the same tension throughout. Some learners always are curious, so what's the function of the pulley over here? The pulley over here is simply to change the direction of the tension force. Here the tension force is horizontal, and here the tension force is vertical. It's the same tension, just with two different directions now. The other thing, especially for the hanging mass, that I've seen some novices actually do. When you have a mass that is hanging in the air, in other words, it's not on a physical surface, there is no normal force acting on it. So when you have this scenario where you have a hanging mass in the air, there's no normal force for this 3 kilogram. There will be a normal force for the 5 kilogram because this is on a horizontal surface. Right, coming back here. There's going to quite likely be a frictional force here. Let's read the question. It says, in the diagram below, a 5 kilogram mass on a rough horizontal surface. That means this object is going to accelerate to the right, which means your kinetic frictional force here is going to be to the left. Is joined to a 3 kilogram mass by a light, inextensible string running over a frictionless pulley. The system is initially at rest. That means your initial velocity is 0. The kinetic frictional force between the 5 kilogram mass and the surface is 4.5 newtons. So they gave you the kinetic frictional force here. It's 4.5. Right, so this one started quite nicely. It says draw a free body diagram of all the horizontal forces acting on the 5 kilogram mass. Why do we not want the vertical forces? They're really not going to be important. So the horizontal forces on the 5 kilogram mass you're going to have your tension acting in the forward direction. And you're going to have your kinetic friction in the opposite direction. You're obviously going to have your gravitational force and your normal, but they don't need that here. I'm going to do the free body diagram for the 3 kilogram as well. For the 3 kilogram, you have two forces acting on it. And please note here, there's only vertical forces on this mass. There's nothing horizontal here. Why? Because this also has a vertical acceleration. It doesn't have a horizontal acceleration. Because it's accelerating vertically, the net force here is going to be vertical. Hence, the vertical forces are important. Here, you're going to have your tension force acting upwards. Very poorly drawn. And you're going to have your gravitational force acting downwards. This is accelerating down. That's accelerating to the right. Please don't put this on your free body diagram, but I'm doing that to actually point out something there. Calculate the acceleration of your system. Again, this is what we would consider to be a typical example with Newton's laws, where they ask you to calculate the acceleration, and normally after that, they ask you to calculate the tension. 4.2. You set up an equation of motion, set up Newton's second law for the 5 kilogram. So for the 5 kilogram, we're going to go F net equals MA. I just want to quickly point out something that I told you guys quite often. If it's accelerating to the right, you let the forces to the right be positive, and the forces to the left will be negative. So your net force here will be T plus minus your Fk. And that equals to MA. We don't know the tension. We know the kinetic friction was given to us to be 4.5. And that's going to be 5A. Now here, because I'm solving for the acceleration, I'm going to get rid of T. So I'm going to make T the subject of the formula. It's 5A plus 4.5. And that's, sorry, 4.5, not 4.5A. And that's equation 1. I'm going to do the same thing for the 3 kilogram. Again, I must point this out because it's accelerating downwards. The gravitational force is positive and the tension is negative here. So F net equals MA again. And this time it's Fg plus minus T equals MA. Your Fg is mg minus T equals MA. So I'm going to draw a little line there so we don't mix the two up. Your mass is 3, G is 9.8, minus your tension equals 3A. 3 times 9.8, 29.4. Take the 3A across, minus 3A. Take the T across, equals to T. There's your second equation for tension. There's your first equation for tension. You now can equate 5A plus 4.5 equals to 29.4 minus 3A. 5 plus 3, 8A. 29.4 minus 4.5. 29.4 minus 4.5, someone?
24.9.
Divide that 24.9, yes.
3,11.
Now, when they say calculate the acceleration of the system, this is a very poorly phrased question. It should have said calculate the magnitude of the acceleration. Because if you have to put in a direction, you're going to have to put in 2 different directions there. Because for the 3 kilogram, you'd have to say that the acceleration is 3.11 downwards. And for the 5 kilogram, you'd have to say that the acceleration is 3.11 to the right. And don't forget the meters per second squared. Now, they generally are not so tardy with the phrasing of the question. They're quite specific. Then it says, describe the motion of the 5 kilogram block when the 3
Sir.
kilogram. Yes, sir.
So you said for the 3 kilograms, you said that Fg was equal to mg, sir.
Yes, sir.
the gravitational force.
Yes, sir.
Oh, never mind. No, wait. Oh, never mind, sir. Never mind. Sorry.
Okay.
Sorry.
Right, so it says describe the motion of the 5 kilogram block once the 3 kilogram block lands on the ground. Now, once the 3 kilogram block lands on the ground, this is what's actually going to happen. When the 3 kilogram block lands on the ground here, there's going to be no tension in the string because it's not going to be pulling on anything because that's going to be moving forward. Remember that. So what's going to happen to the motion of this object on the top if the tension actually drops to 0 here? In other words, what's going to happen is this rope is going to get a bit slack. It's going to get a bit loose. Because as this is moving forward now, this is also not moving down. So the rope is going to kind of bunch up over here. So the tension will become 0. It's still on a rough surface. So your net force will be acting backwards, which will be your kinetic friction now. And it would actually slow down and come to rest on the top. So for 4.3, the 5 kilogram slows down. It comes to rest. Now that was a super easy question where you have a horizontal and a vertical mass. I want to take this one and put it up. All right, what makes this one more interesting than the previous one? You have an externally applied force going to the left. You're going to have your kinetic frictional force here. And you've got a hanging mass there as well. So again, just to clarify a few things, your tension is going to act away from your masses towards your pulley along the string. So there's the two tension forces there. You've got an externally applied force here. That's going to have two components attached to it. Your Fx here and your Fy here. All right, let's read. Now, I don't know in which direction the system is going to move because I don't know how big the tension forces are or whether that 60 newtons acting at an angle is going to be large enough to actually pull the 2 kilogram up, or the system is still going to accelerate to the right and downwards. So let's hope the question is more clear and gives us some clues. So let's read. A 5 kilogram block resting on a rough horizontal table is connected by a light inextensible string passing over a light frictionless pulley to another block of mass 2 kilograms. The 2 kilogram block hangs vertically as shown in the diagram below. A force of 60 newtons is applied to the 5 kilogram block at an angle of 10 degrees to the horizontal, causing the block to accelerate to the left. So the block accelerates to the left, and that's important.
Question, sir.
Yes, sir.
Sir, is this grade 11 or grade 12? Is this
There's
from a
no
grade
such
11?
There's no such thing as a difference between grade 11 and grade 12. So
Bruh.
the reason for this is quite simply because your grade 11 Newton's laws is the same in grade 12. Let me rephrase
Thank you.
this. We don't reteach this section in grade 12. Whatever you do in grade 11 is exactly the same work that's coming out in grade 12. The grade 12s don't do this as an additional section in matric. They revise their grade 11 work at the start of matric. So
Thank you, sir.
one more thing about the grade 11 work. That will actually tell you how important this first term is, which I think most of the grade 11s are taking it as a joke. Your next section, by the way, which is more difficult than Newton's laws, which is called electrostatics. And you're going to try and actually do it in now, I think about a week and a half. If it's harder than than Newton's laws, with a larger variety of questions, and we already have people in grade 11 who are starting to take their work not so seriously, you can imagine what's going to happen to you in the exam. You can ask these grade 12s, by the way. They are not going to be doing electrostatics again in grade 12. They are not doing it at all. Actually, if I tell them I'm doing electrostatics again with the grade 11s, they will actually join you all for all the lessons. I guarantee you this, because they already know from last year how difficult it was. Now, you've got a very, very small window in which to do a very long section. So we're going to actually meet very often to try and finish this, covering a large variety of questions in the next section. So Newton's laws and electrostatics and electric fields is not repeated in grade 12. Whatever you do in grade 11, that's it. It's done and dusted there. If it comes out in grade 12, in your paper, you will have to revise it from grade 11. There's no new work done in grade 12 on any one of those two sections. So it's just completed. Question 2 in your matric exam is completed now. Question 7 in your matric exam is completed now as well. So this is your start of your grade 12, in other words, in grade 11. So
So
we're
you
ready.
answered my question. Thank you.
No problem, sir. A force of 60 newtons is applied to the 5 kilogram block at an angle of 10 degrees to the horizontal, causing the block to accelerate to the left. So if the block accelerates to the left, it means the 2 kilogram has to be lifting upwards and accelerating upwards. Now that's important because it also gives you the direction of the frictional force, which we need here. If it's accelerating to the left, it means your friction is to the right. And also your tension is to the right. So the kinetic friction between the the coefficient of kinetic friction between the 5 kilogram block and the surface is 0.5. So this is a super hard question because they didn't give you the frictional force. They gave you the coefficient of kinetic friction to be 0.5. Draw a labeled free body diagram showing all the forces acting on the 5 kilogram. So I'm going to draw both free body diagrams. I'm not going to draw one. So question 3 here, 3.1. I'm going to start off with the 3 kilogram. Sorry, is it 3? No, 5 kilogram. All right, let's start. I like to start off with the components first because I don't ever draw the applied force. So there's my Fx there. And there's my Fy there. Then I fill in all the other forces, which would be my gravitational force going down, my normal force because I'm on a surface, and then to the right, I'm going to have my tension in my string that I've drawn in red there. And I'm also going to have my kinetic frictional force to the right because it's accelerating to the left. So there's the 5 kilogram. And the 2 kilogram free body diagram is the following. It's not on a surface, so there's no normal. It's accelerating upwards, so the tension has to be larger than the gravitational force. There's no other forces on this. And there's your free body diagram for both the 5 and the 2. They will not ask you for both. But as I said, you will definitely end up using both of the free body diagrams in your calculation. Calculate the magnitude of the vertical component of the 60 Newton force. Now, you see, this examiner is being kind because he's trying to hint that you need these vertical and horizontal components because you're not going to end up using that 60 Newton force at 10 degrees. So 3.2.1, F vertical, which is your Y component, is F sine theta, which is going to be 60 sine 10. Answer?
10,42.
Yep. And F horizontal,
59,88.
thank you.
So it's 0.9.
09, sir. Sorry.
Sorry, just say that answer again.
59,09.
So for question 3.2.2, is the answer negative or positive?
You will only put the answers to be negative or positive when you're doing a calculation, because here they only want the magnitude, sir.
Okay, sir, thank you.
Right, then the next one, state Newton's second law, which we are not going to do. So here's the thing, don't make a force negative or positive. Your positive and negative is simply going to be based on the direction of the acceleration, and also only make it positive or negative when you plug it into FNet. I'll show you what I mean by it when I actually do it now. Calculate the normal force on the 5 kilogram. And the reason why they wanted the normal force here is because they know that the normal force is not equal to Fg. They want the learners to see that on the free body diagram. So here, because there's no motion in the Y direction, the objects are not this object is not moving vertically here. These forces will cancel out each other. For the 5 kilogram, remember there's horizontal acceleration there, which means the vertical forces cancel out each other, which means Fn here plus the Fy there added together will equal to the Fg at the bottom. So to get the normal force, I'm going to say Fn plus Fy equals to Fg. So from here, your normal force is Fg minus Fy. And your Fg is mg. And your Fy, we can simply take it from above because we worked it out. There's a there. Remember, this was for the 5 kilogram. So your normal, 5 times 9.8 minus the Y component, 10.42. 38.58.
Yes, sir.
And again, they just wanted the magnitude. Why do they want us to work out the magnitude of that normal? Because we don't have the friction. And that's why this question here is 7 marks. Actually, it's not, it shouldn't be 7 marks. It should be at least 8 marks. Because there's just too much to do for that 7 marks. So where do you start with this? Because you don't have the friction, always start by calculating the friction, because that's going to help you to set up all the simultaneous equations that will follow. You're going to need it to actually set up the simultaneous. Generally, if you're going to be using something like your friction in all the equations you're going to set up down the line, my suggestion is to either leave it in surd form or as a trigonometric expression, or if you're going to use decimals, use at least 3 decimal places, because it's going to affect your answer quite badly as you go down. So 3.5, I would start off with the kinetic frictional force, because that's the reason why they asked us to find the normal there. So your kinetic frictional force, and this is for the 5 kilogram, by the way. We're not going to put in any direction for it. We're just going to work out the magnitude. The coefficient of kinetic friction is 0.5. And the normal, actually, they asked us to calculate it, so we're not going to get any hectic running decimals, so to speak, because it's basically a question in the paper. So we can take the 2 decimal answer and use it here. So it'll be 19.29, am I right?
Yes.
Yeah.
Now that I got the frictional force, I go back to each one of them and I set up Newton's second law. Remember, this time I want to eliminate the acceleration because I want to solve for tension. So going back, the next question says 3.5. Calculate the tension in the string, not the acceleration. So that's the start of the 3.5. So you have your 2 masses. I'm going to start off with the harder one first, which is the 5 kilogram. I'm going to say F net equals to MA, and this is where the plus and the minus come in. So please listen up. It's accelerating to the left, so the forces to the left are positive. So it's a positive Fx. It's a negative tension added to a negative kinetic friction. So your Fx plus a negative tension plus a negative kinetic friction is equal to MA. That's where the physics ends, by the way, there. After that, it's just maths, because you're going to substitute into this equation. Your Fx, you're going to take it from the top because you are asked to work it out. 59.09. We want to find the tension. We got the kinetic friction. We can simplify this. 59.09 minus 19.29, please. 38.90.
38.8.
80, yeah.
39.8. 39.8.
39.8. Minus the tension equals to 5A. I'll call this equation 1. Then I go to the other mass, which was the 2 kilogram. And I do F net equals MA again. This time, remember, the 2 kilogram is not accelerating downwards. The 2 kilogram is accelerating upwards. So the tension will be a positive force, and the gravitational force will be a negative here. So it's going to be T plus minus Fg here is equal to MA. We want to find the T. That's going to be mg for your gravitation and MA for the right-hand side, which will be 2 times 9.8 equals 2A. That will be T minus 19.6 equals to 2A. Now, the trick is to get 5A in both the equations. This requires a little bit of skill on your part. You need to basically decide what you need to multiply 2 by to end up with 5, and the answer is 2.5. So you multiply the second equation here, right? So it'll be equation 2 multiplied by 2.5. So 2.5t, 19.6 times 2.5, please.
49.
Thank you. Equals 5A. So there's your new second equation. You got 5A equals to 2.5t minus 49. You got 5A equals to 39.8 minus 2t. You now can equate the left-hand side. So 2.5t minus 49 is equal to 39.80 minus t. Two 2.5t plus 1t is 3.5t. 39.80 plus 49.
88.8.
Divide both sides by 3.5 and you got your answer for t.
25.37.
This is not as hard as it gets for the hanging mass. You are all invited for the lesson tomorrow afternoon at 4 p.m. where I'm going to finish off questions with the hanging mass and then start with inclined planes tomorrow. Thank you for all of you attending today. You're going to have a lesson tomorrow at 4 p.m. There would be another lesson at 8 p.m. to finish off Newton's second law tomorrow. Because I'm actually going to finish it off tomorrow night. So I know I'm done and dusted with this. Right, people, I'm going to actually put this up on the different groups over there. You may want to share it with everyone, and I'll put up the link, the video, a little bit later. Thanks for attending.
Bah.
Thank you, sir.
Thank you, guys.
Thank you so much.
So when you're doing electrostatics and circuits with the grade 11s, can we join?
Yes, definitely.
Okay, thank you, sir.
Evening, sir. Sorry to disturb.
Bye, guys. No, it's fine.
So I just wanted to find out, for our schedule, for our first term, it's just going to be one paper, correct?
Yeah, but it's going to be
Because my-
one paper with a ton of work. So
Okay, sir.
organic,
Because my teacher
Newton,
told me.
momentum, and VPM.
Okay. So I don't think we're going to write the common paper, sir, judging by how far we are.
Yeah, it's actually, I don't think any school can do justice to organic chemistry. You just have too little time left. I don't know how the department expected everyone to do so much in such a short space of time. It's just impossible. So I would actually, if I had a choice in my school, I would also I wouldn't do it because we are going to simply rush through a large volume of work now.
Okay, thank you, sir.
Right, guys?
So if you're writing the government paper, are we expected to know the whole of organic syllabus?
Yes. Yeah, I don't know. I don't know how they're gonna do that. Alright, guys. See you tomorrow. Tomorrow at 9, every grade 12s, and then again at 4, and then again at 9.
Okay, thank you, sir. See you.